Okay, welcome back everyone. Today is Tuesday, so let's just continue on static stability longitudinal. Actually, dynamic. Dynamic is really, I'm just going to cover some very basic stuff. It's obviously above and beyond of what this class should cover. Dynamic stability is just the introduction. So let me just start taking your in-class attendance. You got 3 people here. We got 1 person here.
Yeah, we forgot you. You forgot
Good. You're very safe from the rest of the class, completely isolated.
That's true.
That's fine, no problem. I mean, don't worry about that. Okay, so.
Are you trying not to catch COVID?
Well, no, it's just his habit to sit on the corner on the other side of the.
Yeah, that's it.
That's no problem. I mean, don't worry about it. They're joking around.
Yeah,
You joke back, basically.
that's why I said I don't like the.
You don't like to be with those people, right? Anyway, so I guess today and this week, Thursday, we're going to finish up all the lectures. I hope so. And then next week, Tuesday, it's going to be a study day for you guys. And then Thursday, you have exam 2 that actually covers C and D. Yeah, go ahead, question, Jimmy.
Are you saying Tuesday is no class or coming into class for?
I'm thinking of no class. That means you need a study day for exam 2, right?
Oh, no, so I was asking if you're
Tuesday.
doing an in-class review or if it's just like you study on your own day.
Yeah, you study on your own day. That's the study day. I mean, you're not going to show up in class and study, right? Study day is like a study
If
for
you do
yourself.
an in-class review, I will.
Practically speaking, your vacation day. That's the study day, right?
Can you just do an optional review day instead?
Do you need a review? I
Sure.
post all the solutions.
Can we just do a go over in class?
Well, maybe.
Well, I mean, do I need to?
Be nice. We
I don't
pay
think
for it.
so. I mean, those are easy programs. I post all the solutions fully explained. And do you need still review? I don't think so.
Well, could you maybe specify?
I can do that personal basis. In other words,
Sure, yeah,
okay.
sure.
Of course, you can request that. Hey, I have absolutely no clue what you lectured. So give me one-on-one session. I can do that, of course. If I doubt it though. I doubt it, but I don't think anybody needs that kind of stuff.
You know what to do.
But
Just come
again,
up with
Study day, if you absolutely need my assistance for help, to prepare yourself for the exam too, of course, sure. Just request it. Just to send me chat to begin with. Hey, can I call me? Or can I call you? And then, yeah, sure, go ahead. Just call in and then asking question after question after question. That's fine. It's part of my job. So even though I hate to death, I do it anyways.
Oh my God.
I'll do it anyways. I've been paid for it, so sure. But I doubt if you really need such a thing. Of course. I mean, you're a student. I mean, you don't need that. Anyways, so hopefully this is the semester end schedule. So this week we're going to finish up all the lectures, and next week Tuesday is going to be a study day. That means you just spend Tuesday nicely to be ready for the exam on Thursday, or expend that time for some other class. I don't know. Okay. Anyways, do you have any question here? So if you need help, sure, of course, you can just send me chat to begin with. Microsoft Teams. I'll be happy to go over anything. Okay. But again, solutions are posted as I grade it. So take a look at solutions to begin with, because looking at those solutions might answer all the questions you may have. Don't waste your time. Don't waste your time just talking to professors. That could be a huge waste of time, because professor may say more than what you want, right? Of course, true. I always try to say more than what you wanted to begin with. Education process. Okay, so all the solutions will be posted here. So I think everything should be straightforward. I'm not going to create any new program for the exam. I'm not that motivated. All I'm going to do is probably cut and paste, change a little bit. That's it.
Are you actually motivated at all?
Almost at all.
Okay.
But I may change the numbers. I may or may not. I don't know. It depends on my mood. But exams should be very straightforward, something you have seen it, you have done it, something like that. Any question about schedule? End of the semester schedule. Let's wrap it up nicely, okay? So I think one thing you have to be working on right now is phase 3, which is the entire airplane configuration for performance computation. Performance computation requires certain data points. How powerful your engine should be. Actually, one of the teams, I realized that the team is glider. That means you don't need a propulsion, technically speaking. So all you need for the performance computation is minimum sink rate and then also maximum gliding range, right? So you can stop there, but the other team may look at it saying, hey, that's so shabby, you know, there's no, I mean, so if you want to avoid that kind of image from other team, you can do like a what if we put this motor and engine off the commercial off the shelf, if it's attached it, what is the range could be, you know, you can easily compute such kind of things. Okay. So I would encourage you to do that if you want to. All right. So anyways, all the things come down to phase 4 presentation that actually replacing the final exam time. It's only 10%, but you're going to present whatever you design throughout this semester. It is going to conclude your design. And then this is going to be peer reviewed also. Peer review score comes in. So if your team did extremely poor job, that may negatively impact from the peer review score points. It's not going to be like, I'm not going to flunk you anything, but it may impact as a maximum impact of 10% range. That means you expected A, it could drop to B, but it's kind of highly likely unless you are on the borderline. So the question is, you are 89.999 expecting to have A, that means, hey, let's do a good job in final presentation. If you do a poor job, I guess that's it. You deserve B, that's it. You're B anyways, and there's no complaint. That's what it is. Okay? If you're happy with B, just to do a crappy job, that's fine. You keep your B. So it only affects on people on the borderline. Okay? In reality, I'm not gonna drag you down A students to B range. No, I'm not gonna do it. Okay. Any question? Anybody do a good job on exam and final presentation? Go ahead.
Did you say we have extra credit for doing the?
It's not extra credit, but it's gonna be announced next week.
Okay.
Because it's gonna be last week. So I'm going to think about if you participate, professor evaluation process, you know, by the end of the semester. If you participate, I give you some bonus. I'm kind of getting tired these days, but since I'm not that interested, but I'll do it anyways. Out here, of course, still students' voices. Nowadays, I'm kind of getting less and less interested. They say anyways, and then I don't care, kind of thing. You know, it's like a routine. There are interesting comments, you know, oh, you know, Dr. H, he's a Nazi, you know, he controls everything. Wait a minute, I'm Japanese. Yeah, right. So that kind of comments, I enjoy reading it, but you know, it's not going to help anything. Yeah, students make fun of it, just writing those comments. And I laugh at it, but does it help? No. It's entertainment, but not helpful. But suppose if you write nice things such as, oh, you know, his class is always recorded, so I don't have to show up on anything but still get A, you know, that's good. If you want to say that, you can say it. If it's true, I'm going to continue, okay? So I'm kind of interested in hearing both good and bad, both ways. Okay. So let's just move on. Okay, so today we are going to take a look at longitudinal control analysis, which is pitching control. And then unit D2 is the other two controls. One is yawing control, the other one is rolling control. Okay, stability and control, and two more directions going to show up in unit D2. Unit D1 is longitudinal control analysis because without it, at least airplane can never fly. You have to make it at least longitudinally stable. Okay, so that airplane is not going to go right into the ground. Okay, that's not airplane anymore. It's a rock or something. Now, the rest of the concern is as you fly your airplane steadily in longitudinal direction, it may go all the way to right or rolling like crazy, but still flies, right? So that's essentially when we talk about paper airplane contest for high school, for kids. Hey guys, you need to at least make it longitudinally stable, otherwise your paper craft go right into the ground and you cry.
Can we do that for study day?
Huh?
Can we do a paper airplane contest for study day?
Do you want to bet your everything on the paper airplane at the very end of the semester? If your airplane fly like this, you get F kind of thing?
Yeah.
No, just for fun.
Just for fun?
No,
No, no way. Dr. Ashwas may do that. He actually forces everybody to create a balsa wood airplane for stability control. Well, this class, by the way, he developed. And then some people may complain all the way to president. If you get an F because your balsa wood didn't fly at the end of the semester, you get F for flight mechanics class. This is totally unfair. Then president may say, I don't think so. Anyways. Yeah, let's move on, okay? I really need to cover the material. So today's subject is a pitching control analysis, which is essentially, okay, if you look at the diagram here, you're going to apply essentially equation you saw long time ago. When? Statics. This is essentially statics equation. Summation of the moment, if you take it, moment, summation at the center of gravity right here, moment should be sum up to 0. Then it's called the trim condition of airplane. Okay, and also if you sum the forces in vertical direction, it must also be 0. Okay, you're not gonna lose your altitude. You are going to have a steady level flight without pitch up or pitch down. You maintain your altitude. Those two are the equation of equilibrium, which you learned all the way back in statics class. So those are the two equations. So based on that two equations, okay, you're going to determine the sizing and also control authority of your control surfaces. Control authority means the following, okay? If an aircraft's geometry and flight conditions are known, then the lift coefficient required from the wing and pitch control surfaces such as tail, horizontal tail, right? So this is a lift of your main wing, and then also at the same time, the lift generated from your tail surface, LT. Those can be computed based on the flight condition. Of course, the flight condition includes the airspeed or density of air, stuff like that, Q, essentially. And then, of course, you're going to have a maximum value of lift coefficient you can develop on main wing and tail. That is going to be a limiting factor of how much control you can have. So suppose, even though your tail is generating maximum lift based on the CO max, the choice of your airfoil, you really cannot control your airplane. That is going to be not enough control authority. Sometimes this actually happens. So oftentimes you have to do certain things, either increase the sizing of your horizontal tail and control surfaces, or very interesting remedy. Did you notice this picture F4E? So this F4E, the horizontal tail, doesn't have enough control authority. So they actually did the last minute remedy, which is they made leading edge slots for this horizontal tail. Have you ever seen this? Actually, interestingly, I was like, okay, so is there any good picture for such a thing? This is the picture of F4E horizontal tail. Look at that. This is the remedy. Just increase of maximum CL because we needed to have a control authority with the penalty paid for increased drag. But engine is strong enough, who cares kind of remedy. Interesting. So this is another picture here. So this is a leading edge stabilizer. Actually, struts, okay, added to, okay. So this is what I'm talking about here. Stabulator leading edge struts. Yeah, FOE, okay. So to remedy this situation, if you do not have enough control authority, sometimes you have to do something. You have to sort of modify your ground section, in this case, adding the strut. Adding the strut may possibly give you some side effects, such as increase of drag coefficient, may be easy to separate. I don't know, flow is turbulent. There's so many things. It could be a side effect, but at least you can have enough control authority. Okay, so this is one of those examples here. So next page, let's just take a look at example D11. This is insanely easy example. By the way, before we look at this example, have you ever seen this airplane? Do you know this? If you go to a school in Kansas, I went there, Wichita State University, right next to Beechcraft. This aircraft was flying all the time. So we kind of get used to it. Back in when? 2000, early 2000s to 2000, I don't know. I still remember when I was a graduate student, you know, this airplane is always flying. So noisy. Because airport is right next door, so it's always like a takeoff, touchdown, low altitude flight. It's interesting noise, you know. This is the dual turboprop and the huge canard configuration. This is almost 100% composite. Lots of new technology implemented. Never made it to the market, but interesting design anyways. Starship, okay? So let's think about that. A design concept for a light general aviation aircraft uses a canard configuration. Both the wing and the canard of this airplane, by the way, there's a team actually using canard configuration. Where are they? Okay, he's there. Is it working? I mean, X5 is actually computing those things? I'm not sure. You guys can find out those and report back to the rest of the group, right? I'm expecting. It could be interesting to see that. Okay, anyways. Okay. So the aircraft has a mass of 1,500 kilograms, and it's designed to fly as slow as 30 meters per second at sea level in level flight. This is actually a very difficult requirement. Airplane's capability to fly as low as this much airspeed without stalling is aerodynamically actually challenging. Aerodynamically speaking, it's actually easier to fly faster because you have lots of advantage aerodynamically speaking. One of the most difficult thing about airplane is flying slowly without any stall. Still, you're going to maintain low drag and cruising condition, which is very difficult. So this is one of those conditions. At this speed, its cambered main wing generates minus 1,000 Newton meter of pitching moment about its aerodynamic center right here. By the way, let's just mark the aerodynamic center of the main wing, usually quote unquote right here. Okay. So this is AC of a main wing. And then here is AC of canard. Okay. So moment is developed at around main wing AC minus 1,000. That means this is a nose down moment, obviously. Minus meaning nose down. So this airplane has a tendency to pitch down as you slow down to 30 meters per second, 1,000 Newton meter pitching moment, nose down. So in order to compensate, your canard creates enough lift to make it zero moment total at center of gravity. That's called trimming. Okay. So let's be careful about that. This is the trim condition. Trim is summation of the moment taken at CG must be equal to 0, and summation of the force in perpendicular direction is also 0. So this is called the trim of airplane. So this is finding the trimming condition. Can this airplane trim at 30 meters per second airspeed? If you want to achieve the trimming condition, how big your canard should be? Okay. So let's say maximum lift coefficient of its canard is 1.5. So how large your canard area should be? Okay, let's find out. This is actually quite simple. So starting from this trimming condition, you're going to some moment at center of gravity. And then you're going to set equal to 0. So this is trimming condition. So obviously this weight is going through the center of gravity. It does not create any moment around center of gravity. But main wing creating the lift, this is going to create pitch down tendency, and also at the aerodynamic center also create pitch down tendency. So you have a double negative pitch down tendency. So let's just find out moment at the AC. This is negative 1,000, and also another negative lift force. This is the distance difference between XAC minus XCG. This XAC minus XCG is 3 meters, of course, here. Okay. This is the 3 meters. This is negative 1,000 Newton meter. Yeah. So those are the two pitch down, nose down tendency moment around center of gravity. You need to compensate this against the lift generated from canard, which is plus pitch up moment. So this is going to be lift generated by canard LC times distance LC, which is 8 meters. Right? Okay. So this must all become 0. This is going to determine okay, so let's just move on. 0 equal to minus 1,000 Newton meter minus lift times 3 meter plus LC times 8 meter. Okay, here. So this actually gives you a relationship between lift and lift generated by canard. So lift of main wing is lift generated at canard ratio of 8 meter over 3 meters minus 1,000 Newton meter over 3 meter, which computes 2.67 lift of canard minus 333 Newton. So this is one of the relationship. Let's call this equation 1. Okay. Still have two unknowns. How much lift of main wing you have, how much lift of canard you have, two unknowns. So you are going to bring up another equation here. Summation of the force in perpendicular direction must also equal to 0. So this is going to give you lift of the main wing plus lift of the canard minus weight of the airplane must be equal to 0. So lift, let's substitute equation here. This is what? Lift is 2.67 LC minus 333 Newton. That's the lift. Plus LC. W is equal to mg. So this is 1,500 kilogram times gravity, 9.8 meter per second square. This is the weight of airplane, right? Mg. W equal to mass times gravity. Okay. So from here, you can get lift of the canard required, which is 15,033 Newton over 3.67, something like this. It is going to compute 4,096 Newton. So this is the required lift of the canard. Okay. By given condition 30 meters per second, so how much how much area you need for canard. So noisy. Let me just shut down stupid IT's computer in this classroom, just screaming all the time. I don't know. Okay, so noisy. It's not doing anything, but just screaming, the fan. So this is the 30 meter per second required trimming condition, okay? So from here, let's find out the dynamic pressure Q. Q is equal to 1/2 rho V squared. So 1/2 comes in. Density sea level 1.225 kilogram cubic meters, 30 meter per second. This thing square. So dynamic pressure for trimming condition is 551.3 Newton per meter. Newton per meter square, sorry, Pascal. Okay, so this is dynamic pressure. So due to the fact that lift is equal to CL of the canard times Q times SC. Let me just write it nicely. So this is CL over the canard, surface area of the canard. So what we want is area of the canard, SC, which is equal to lift required for canard divided by CL of the canard, Q. Okay. So we plug in 4,096 Newton lift required. CL of the canard is maximum given 1.5, isn't it? Yeah, that's right. So this is the maximum CL the canard can provide, CL max. So let's just plug in 1.5 here. Q, we computed 551.3 Newton per meter square, Pascal. So if you finish that computation, required canard surface area, this is platform, 4.95 meters squared. So it really depends on the rest of your airplane configuration, but it is fairly large size canard required. If you take a look at Beech Starship, this is the canard. Of course, the canard actually comes with control surface. It could be an entire canard is moving, or canard has its own aileron or something. I don't know what's the name of the aileron of the canard. I'm not sure. Air canard or something. So there must be some unique name of it. Because usually canard is the entire surface moving, but in this case, it could possibly have a huge fixed canard with control surface attached to it. I don't know. It's just a design, so don't worry about it. So this is the quick computation in order to have a trim in lowest speed end. Now this one alone does not necessarily determine the sizing of the canard. You have to do constraint analysis to make up the final size of the canard. In other words, we did the constraint. If your airplane comes up with certain constraint, the sizing of the canard must satisfy everything. And then you ended up knowing that the canard is so big and then add too much drag and it's no longer a sport airplane. I don't know. You may find out those things too, okay? So there's nothing wrong for that. Any unique solution, unique discussion, welcome for phase 4 stage. So I hope you enjoy designing airplane. That's what I'm like. Okay. So next thing is, let's talk about longitudinal static stability and a little bit of dynamic stability, not much, okay? So static stability is at least very important, required, because if airplane is not statically stable, you cannot fly manually, period. You have to have some computer-aided control system. So let's avoid such a thing, okay? So first of all, criteria. So this is the criteria to say your airplane is statically at least stable. That means one thing. So this is something called the trim diagram. You are going to plot x coordinate This is an angle of attack absolute value. This is alpha minus alpha 0 lift, by the way. So this is absolute angle of attack you can use. Okay, it could include minus value to the positive value. Absolute angle of attack. I think we defined, okay, in somewhere. Absolute AOA. Did I define in unit B or something? I think I did. Okay, I hope so. So this is plotted for the CM taken at the center of gravity. So this is Cmcg, absolute alpha angle of attack plot. This is called trim diagram. Okay. Now trim diagram could also possibly be plot of Cmcg against CL. Okay, that's also okay. It's a fairly equivalent. However, the advantage of this trim diagram is you can determine this point. This is called alpha trim. In order to have a trim condition, how much alpha diffraction you need for your control surface. This actually determines your sizing. So this is kind of useful. And also at the same time, here, this value is called Cm0. This is a moment coefficient at the 0 lift. If your airplane is producing absolutely 0 lift, how much moment is developed at developed at the center of gravity? That's Cmcg. Cm0, moment coefficient at the 0 lift. Okay. So by looking at the trim diagram, if you claim your airplane to be stable, this Cm alpha must be negative. This is called longitudinal static stability criterion. If the Cm alpha is positive, there's no way you can say this airplane is stable. This is the case here. This is unstable. Okay? And also this is stable. Not unstable. Okay, sorry. This is a stable. Now also another criterion here is in order to have certain value of trimming, okay, this location must be above 0, isn't it? If you start from here, you're not going to have a trimming angle of attack determined, okay? So this is immediately, you can get that from trim diagram, okay? So first of all, Cm alpha is 0 for stability. It follows that Cm0 must be greater than 0 if the aircraft is to trim at a useful alpha trim, okay? So those two are required. Cm alpha is negative, Cm0 must be greater than 0. So this is very healthy trim diagram, starting from some positive value, negative slope. Usually this is linear line, okay? So in order to analyze the static stability, you have to show this trim diagram. Without this trim diagram, no one can say this airplane is stable. So this is at least the minimum requirement at phase 4, okay? All right. So next page, let's just take a look at the neutral point and static margin. Do you remember the aerodynamic center defined for airfoil? That is the location where if you pitch up, the moment developed around is independent to it. That's called aerodynamic center. Aerodynamic center is the location where you put your lift so that you can analyze stability for your airfoil, airfoil alone. Now, you can determine such a point for entire airplane. That's called neutral point. Okay. So neutral point is the terminology used for entire airplane. So this is sort of like aerodynamic center for entire airplane. Okay, this is where you put the total lift of your airplane. You just place that lift at that location of neutral point. Now, obviously, if the neutral point is located on the center of gravity right here on top of it, that airplane is neutrally stable. So just about the difference between neutral point to the center of gravity is going to determine how stable you are. This is called static margin. SM. Obviously, you know those things. I feel like I'm dumb. Everybody in this classroom already know that. Okay, right? Just double checking. Of course you know that. Of course you know that. Yes, yes, yes. So number one question after you design your airplane and present, and people ask you, okay, so where's the neutral point? What is static margin? Is it a good number or bad number? So those are the typical value of static margin for lots of different airplanes. So this is the Cessna 172, one in flight line. Static margin is 0.19, which is fairly big. Boeing 747, this is passenger jet. Of course, you need to have a stable airplane. No one wants 747 to have a combat maneuver. No, you don't need that, but airplane need to be stable. So this is very large static margin here. But at the same time, those are the airplanes that no one expects you to do like a very steep maneuver capability, right? So the fighter jets, on contrary, those will be very, very small body or could be small negative. This one could be very large negative. This is insane design, but X-29. Yeah, this is the experimental airplane that actually focused on maneuverability, right? So again, this is intentional, but typically, either very small value or small negative, but later on they even changed it to slightly positive. So again, it's a trade-off between static margin to the maneuverability, how stable your airplane is. If airplane is too stable, it is very heavy to move. That's acceptable for certain type of airplanes. That's not acceptable for certain different type of airplanes. Okay, and then as you take a look at the shifting of center of gravity, of course, center of gravity can be changed, right? Cargo airplane, you can actually put stuff on the rear, shifting CG aft. That's a very bad terminology. Oh, you are shifting CG aft? What do you mean? Your airplane is now unstable, right? So CG aft is a very bad term anyways, okay? Because you're actually creating unstable airplane. So if you have a cargo, you better start putting up on the front. By the way, I think I took you, Jessica. There's a guy in airport who's building World War I French airplane, biplane, okay? Fairly interesting person. He goes to the same church with me, so he took me to the airplane, and I invited you too. And then he realized that, I measured all the locations of the center of gravity is right here. This is my cockpit here. This is the seat here. If I said myself, airplane is actually slightly unstable. Neutral point shift too much aft because I'm gaining weight nowadays. I'm too fat. So I'm concerned about what is this? What is the static margin? I computed static margin. It was again slightly negative value. So he said, well, I can maneuver it. I'm an experienced pilot. I can probably do it, or should I go for diet? Do something. Then I said, do you have a ballast or something just to put it, forward a little bit? Then guy said, no, absolutely heck not. Well, that's a typical pilot. I'm going to lose the efficiency. I'm not going to put any ballast. Well, wait a minute. The stability is more important than efficiency. Because stability, you may die. Efficiency is right. More airplanes kind of using more fuel, sluggish to take off and stuff, but who cares? Anyways, so it's an interesting side story. By the way, he did the flight test. He hired someone else. He didn't do it by himself.
Yeah, so
And then, it was very jerky airplane to fly. So lots of revisions right now going on. Okay. Anyways, entire airplanes made by wood, World War I type. It's a French what? I can't remember the name. That's very classic World War I French design airplane. It's like he was motivated after that. The guy's name is on the airport, right? Ernest Rubb. That's the airplane he flew. He did the World War I. I think Army Air Group is sent to France So that's the airplane he designed and built. It's actually not the full scale. It's like 1.8 shrunk, a little bit shrunk, smaller size airplane. That's also an adverse effect. Your airplane's not that, it doesn't have much factor of safety because it's smaller airplane and he's bigger man. It's not a good combination. Anyway. So next page is, okay, so if that kind of thing happens, how can I make it better? Let's alter longitudinal static stability. And then most of the discussions here, you know, in reality, hey, how can I do it? It's almost like rebuilding a new airplane. How can I do such a stupid thing kind of discussion? Also included here, okay? But if you do such an alteration of longitudinal static stability, this is nightmare, as you can see, right? Equation all of a sudden kicks in. So one of the equation is, so this is the governing equation of Cmcg. Cmcg is a function of so many things. Things to look at is how much moment coefficient at aerodynamic center is developed, first of all. So this actually has something to do with what kind of airfoil did you choose to begin with. So this is like, how can I change? There's no way, you have to build a new wing or something. So again, some are acceptable, some are not acceptable. CL alpha, this one too. It all really depends on what kind of cross section, what kind of wing did you build. You cannot easily change those things, alpha too. So this is something you can alter. In other words, location of the main wing attachment. In other words, this is a shifting of CG location to the main wing aerodynamic center. You can sort of change it. Easiest change is put the ballast, but the guy, hey, heck no, I'm not going to do it. This is a tail characteristics. Again, it depends on what kind of tail did you have. This is design characteristics. It's not easy. This is a downwash. In other words, location of your tail, is it inside of the downwash here or there? Or you can completely avoid the downwash wake region. This is how big your tail volume is. Again, or you just to make the tail bigger, to make it stable kind of thing. This is incident angle. It could be an easy fix. However, if you put more incident angle of the tail, you may have a difficult time trimming, in other words. So everything comes with something else. Everything is interconnected. So this is, by the way, next page also have an equation. So this is the, how can you alter it? Cm0. Cm0 is a function of, again, aerodynamic center Cm plus tails characteristics of the lift, downwash angle, and tail volume. This is a Cm alpha, the slope. You can make the slope steeper if you want to, but how can you do such a thing? Well, of course, bigger volume, bigger volume of tail, or changing the 1 minus delta dE alpha. This is downwash. Once again, location or positioning of your tail comes into play here. And this is the shifting of the wing main attachment to the relative to the center of gravity. So either you change the attachment point or you change the center of gravity. Easy one is changing center of gravity by just putting some weight on the front. Make it top heavy, not the tail heavy. Or change your seat position to the push it forward and then, whoa, I can never fit in because I'm too fat kind of thing. So again, everything is relative. Okay. So this is just a summary thing, okay? So this is a summary of how can you make your airplane more stable. So those are the summary of suggestions to the airplane designer. Hey, you know, I'm an aeronautical engineer. Those are the list of suggestions. Some of the things can never be accepted. Some of the thing is more realistic, but heck, I don't want to kind of thing, okay? So you can change, can you change CL alpha? This literally means that to make a new wing. So the guy may say, what are you talking about, right? XCG, XAC, those are the relative shift of center of gravity, AC location. This is typical choice, right? Obviously, you can do certain things here. Tail volume, of course, make a new tail. Then the guy may respond, well, what are you talking about? How much cost does it take? Well, you were talking about my original design was not very good. The bottom line is, yeah, but it's hard to say and accept, right? this one too. And then this is the positioning of the tail. In other words, downwash, is it going to be like a position of the tail is under the heavy impact of downwash? If so, you have to change the positioning, but it's not easy because it's like a change of design of fuselage and attachment point, lots of other things, controlling other things. So anyways, having said that, let's just take a look at the example D12, interesting example here. Okay. So this is how you make your airplane more stable. There are certain things you can do, certain things you can never do. There are things that it's going to cost a lot of money. There are things like, hey, just to put the ballast and changing CG, the heck no, I'm not going to do it. Kind of, airplane is essentially carrying always the dead weight. It's just an image of how poorly designed your airplane is. So I cannot take it as an image. Anyways, so lots of things, okay? So let's take a look at the page 11, example D12. A conventional tail-aft flying model aircraft has the characteristics shown. Here is the characteristics data, wing and tail and airplane itself. Okay, what is the aircraft's trim speed, the speed at which it will fly in equilibrium at the sea level? What would happen if the aircraft were launched at 15 feet per second? In other words, this is the launching situation of launching. Suppose if this airplane at the sea level has certain trimming airspeed. In other words, if you fly this airspeed, your airplane is completely perfectly fly straight. If it's paper airplane, it's a nice, beautiful level flight. Everybody is dreaming of kind of thing. Suppose if you fly faster speed, what happens is it's going to climb up and then hit the ceiling and come down and try to climb up, and then after a while it is going to trim into the level flight if it's a stable airplane. Okay, so we are going to find out those things. Okay, so we are going to begin with the trim diagram by definition. Okay. So trim diagram is already defined, so let's just review for that. The important thing is you are going to plot Cmcg against absolute alpha, angle of attack. You are going to have this kind of plot. So make sure when you present phase 4, you need to show the trim diagram. And then trim diagram is going to get you three important things. This position is Cm0. Okay, zero moment. What's the name? Cm0 is terminology-wise. The moment coefficient of zero lift. Okay, so zero lift moment coefficient Cm0 right here. This is alpha trim. So this is a required trimming angle of attack in order to have a trim condition. This is the slope of this curve. This is by definition dCmcg, the alpha absolute, which can be defined by Cm alpha. Okay, so this is the center of gravity moment curve slope. Similar to, do you remember CL alpha? This is a lift curve slope. CL alpha T is a tails lift curve slope, stuff like that. But very similar notation. This is Cm alpha. So this is center of gravity moment curve slope. Okay. So those are the similar notation. So this is a trim diagram. Okay. So first of all, let's find out tail volume ratio. So tail volume ratio as defined, B sub H. So this is essentially how big your tail really is, effectively speaking. Let me just zoom in a little bit. Okay. So tail volume ratio is S of tail, L of tail, divided by S times C over bar. So this C over bar is mean code of a main wing. Something called MAC, okay? Mean aerodynamic code. We're going to cover that later, okay? So those are all given as a data set. S tail is 0.3333, 0.3333 feet square. And then, what's LT? LT, this one, 1.2 feet. Area of the wing, S is 0.8 feet. Code ranks 0.4. This is main aerodynamic code of the main wing. Okay. This is going to compute 1.25. Okay. Tail volume ratio 1.25. We found that. Okay. Next step is, let's find out Cm alpha. Once again, this is the center of gravity moment curve slope. This is CL alpha times Xcg. This over bar is normalized by the code ranks, okay? XAC over bar. So this divided by code ranks is over bar, okay? Let's be careful about that. Okay. Minus CL alpha of tail, 1 minus d epsilon d alpha. Is it given? Yeah, it's given. D epsilon d alpha 0.2. So this is the effect of the downwash or angle of attack. And then multiply by BH. You can actually simplify. Well, no, okay. Note. X over bar is essentially X over code ranks, okay? For each center of gravity and aerodynamic center. So let's just plug in here. So you are going to plug in C. What is CL alpha? CL alpha 0.078. Unit is per degree. Xcg is Xcg divided by C. So this is 0.2 over 0.4. As a result, unit goes away. Okay. X over by AC is XAC 0.1 foot divided by 0.4 foot. As a result, unit goes away. Minus CO alpha of tail is given 0.068 per degree. That's right. Multiplied by 1 minus d epsilon d alpha 0.2 effect of downwash times volume ratio 1.25. So this is going to give you Cm alpha, which is of course negative. You have to 0.0485. Unit is per degree. Be careful, this must be negative, otherwise it is unstable airplane, okay? So you got that. All right, next step. Next step, you're gonna find out Cm0. This is a zero moment, okay? Cm0 is zero moment. What was the name? I keep forgetting. Cm0 is moment coefficient for zero lift. Here we go. Zero lift moment coefficient around CG, Cm0. How can we get Cm0? This is given equation Cmac plus CL alpha tail times epsilon 0 plus incident angle of tail, IT, times tail volume ratio, BH. Now, one thing quite important here is this is the downwash at the 0 angle of attack. Let's assume about 0. Okay, it's very small value. So let's just plug in the rest of it. We found the CMAC. CMAC is a given. Oh, okay. CMAC of a wing body. Okay, minus 0.04. There we go. So let's just plug in minus 0.04 plus CL alpha tail is 0. CL alpha tail 0.068. That's right. 68 per degree. That's CL alpha tail. This is 0 plus incident angle IT. What is it? Yeah, 4.8 degrees. Okay, here we go. 4.8. That's IT times tail volume 1.25. So this is going to give you just a number, right? 0.3. Because the degree and per degree cancel each other. This is zero moment, zero lift moment. Okay, moment for zero lift. Okay, that's right. Next step is, okay, let's find out alpha trim. How can we get alpha trim? You need to go back to this figure. How can we get this alpha trim? So alpha trim is basically the definition of Cm alpha is, okay? So this is how much Cmcg change happens over the given change of alpha absolute. It's just the slope, okay? So if you take those two locations to determine this slope, this is going to be essentially negative Cm0 divided by alpha trim, right? You are taking this point and that point, assuming completely linear line. This is the slope. Slope is negative. Do you follow? This is a linear line. Okay, anyways. So from here, okay, alpha trim can be given from here direct. This is going to be, okay, negative CMO divided by Cm alpha. So let's just plug in those things. Cm0 is 0.3, so negative 0.3 divided by this Cm alpha, which is minus 0.0485. The unit is per degree. So the result is 6.186. Inverse of per degree is degree. Here we go. So this is alpha trim. So in this airplane, in order to have a trim condition, you have to deflect alpha of a tail 6.186 degrees. Okay. Actually, no, this is angle of attack for trimming condition. Sorry about that. Okay. So for this trimming condition, what is the CL? For this trimming condition, CL can be computed. CL is equal to CL alpha times alpha absolute. In case of trimming, CL alpha times alpha trim. So for a flight of 6.186 degrees, how much CL do you need for a trim condition? So this is 0.078 per degree of CL alpha multiplied by trimming 6.186 degrees of alpha trim. Oh, you need the CL for 0.482. Here we go. So, how much lift do you need for level flight? Level flight means lift is equal to weight. Weight is given, okay? So, lift is equal to weight is equal to CL times Q times S. Do I have a Q? Q. Did I compute Q? I'm not sure. Okay. Yeah, let's compute Q. Q is 1/2 from V squared. Oh, actually, no. Let's go back to it. So from this relationship, you can compute Q out of it. Q is equal to weight divided by CL S. Let's just plug that in. What's the weight of airplane? 0.03 pound. What the heck is that? This is like a balsa wood, maybe. Okay. So now we are talking about balsa wood airplane. Now I realized this must be Dr. Ashworth. Maybe because of Dr. Ashworth, he left it. Balsa wood comes into play at the end, kind of thing. So CL required is, of course, we know 0.482 for the trimming condition. 0.482. Wing area. 0.8 feet squared. Yeah, that's right. This is balsa wood. So this kind of thing. Balsa wood. Okay. 0.8 feet squared. So this actually computes the Q, dynamic pressure required for this trimming condition, 0.0777 pounds feet squared. So this is Q. So from here, you can determine the velocity for trim. This is square root of 2 times Q over area S. So let's just plug in all of those values here. Suppose if this is the second exam problem, it's a nightmare, isn't it? 0.777 pounds per feet square. Can you handle this kind of exam? Sorry, don't be quick. 2Q over rho, isn't it? Sorry about that. Okay. So rho as a standard sea level density 0.002377 slugs per cubic foot. That's right. This is going to get you 8.09 feet per second. So this is trimming speed. That's what I wanted. Okay. So trimming airspeed. Okay, 5 more minutes. So let's just wrap up what we've been doing. So this is, let's imagine this is Dr. Ashworth's flight mechanics class. This is the final project. He gives you, okay, well, design and build balsa wood airplane. Here we go, and then launch it with a trim speed. If you launch it exactly 8.09 feet per second, it is going to fly straight. Very beautiful. And you get A. So this is the computation behind it. Okay? I suspect he probably did it last semester. So this is the information given. Okay, make a balsa wood airplane. Make it completely trim flight. This is the computation required. Okay, do I do that? Well, probably not. This is too maniac. Anyways, so suppose, okay. So suppose if you launch this airplane, V equal to 15 feet per second. That means this is higher than trimming airspeed. So what happens is you launch the airplane, bounceable airplane, with faster than trimming airspeed, 15, okay? This is going to go fly up like that, and then coming down like this. Eventually trim at 8.09 feet per second. In other words, your airspeed slows down because of the drag buildup. You're going to slow down to 8.09 feet per second. Now airplane come into the steady level flight. That's the trimming condition. So that means the following, okay? Lift at 15 feet per second launch, CLQS. This is the CL times 1/2 rho V square times area S. If you compute the same CL, 0.482 times 0.5 times rho is rho, velocity is 15 now, right? Then area is the same, 0.8, right? So lift is going to be 0.103 pounds. Okay? So you can determine the load factor N, which is lift produced over W. So lift, you actually produce 15 feet per second, 0.103 pounds of lift you produce. Weight of the airplane, 0.03 pounds. So this actually computes the load factor 3.44. So if you launch with 15 feet per second, you are going to have 3.44 G climb. And then climb down and climb up a little bit, and then eventually slow down to 8 feet per second, which is trimming airspeed. So your airplane is going to go up and coming down and fly like that. Okay. If it's a stable airplane, obviously. Okay. So let's just stop here today. Okay. So Thursday this week, we are going to finish up Unit D1 and then hopefully also finish up Unit D2. Unit D2 is yawing and rolling stability. Okay. Static and also a little bit of dynamic. Any question here? All right. Have a good day and see you back on Thursday.